Hi viewers, welcome to all. Here we are discussing about a project ER-TCAM, a soft error resilient SRAM-based ternary content-addressable memory for FPGAs. In a software-defined networking, in packet classifications and open flow applications which using static random access based ternary content-addressable memory on field-programmable gate array. Thus, SRAM-based TCAM will using major part in FPGA-based applications. It will support to reduce a vulnerable to soft errors with a high search performance and a reduce critical path delay. In brief, SRAM-based TCAM will reduce the cost and reduce the response time with a single bit parity fault detections, which also covered minimal critical path overhead. Okay, so thus this technique exploits the binary encoded TCAM table maintained SRAM based TCAM for updated purpose to implement a low response time error detections. Thus the proposed work of this paper will present a SRAM based TCAM using error detections with error corrections with different TCAM sizes. Example 64 x 40 and 512 x 40 and 1024 x 40 and 2048 x 40. Finally, this work will designed in Verilog HDLs and synthesized in Xilinx Vertex FPGA and prove the performance of area, delay and power. Okay, so now we can verify this base paper. Okay, so this paper maximum size they are designed is 1024 x 40 size of TCAM. Okay, and they are designed Artix-7 FPGA, but in this proposed work we are designed 2048 x 40 TCAM size and we are designed a Vertex 5 FPGA. Okay, so here section 2 will mention SRAM based TCAM on FPGA. Okay, and figure 1 will be mentioned the simplified implementation of the TCAM using SRAM. Here the 4 x 4 TCAM architectures will be given. It will be searched with a different search key size and it will be compared with the AND gate operation. Okay, so here the AND gate operations will be functionality with 0 0 means output is 0 and 1 1 means output is 1, so we can identify the data will be easily. Okay, that's why they are using AND gate operation here. For XOR gate operation it will be detect error corrections and error detection easily, that's why we are using XOR here. For this XOR operations we will be choose some other reference paper also, error detections and corrections in SRAM emulated TCAM. Okay, here you can verify this architecture also will be designed with a different key size and finally they will be matched with the XOR operation to detect the error. Okay, the same operations will be handled on here also. Okay, so number of bit will be XOR here. Okay, and figure 3 will be mentioned the proposed ER-TCAM architecture for error detection. Okay, so here this is a single bit operation based architecture. Okay, in the single bit operations initially they are written the data, okay, in the SRAM memory. Okay, so once it will be written, okay, the data will be read out and it will be compared every data, okay, in using this AND gate operation. Okay, and parallelly XOR gate operations. Okay, so in this XOR gate operations will given an error signal to N2 log N encoder. Okay, so it will provide the address to the output of figure 4, the proposed ER-TCAM error corrections model. Okay, so this is a error detection model and this one is a error correction model. Okay, so once the output will be generated, match information registers, base address registers and bit pattern register, thus output will be given to this model ECV. Okay, so ECV computation unit. Okay, so here the search key will taken parallelly using this log square and operation. Okay, this is a multiplexer. Okay, based upon the SRAM memory, okay, we will be divide the address sizes on here. Okay, and it will be taken from bit pattern register. That bit pattern registers will be used it on here. In the figure 4, the proposed ER-TCAM error correction model, initially it will be generate a AGU unit. Okay, address generation unit. It will generate the address and also data. Okay, and it will be initially written into the SRAM memory. Okay, so once the written operations will be finished, the SRAM data will be read out. Okay, and match with the information register. okay, and this is a matching model, okay, for comparison of two data, okay, and parallelly the parity checking also happen here, okay. So once the parity bit will be matched, okay, the match bit will be come out of the TCAM architecture, okay. This is the functionality of this ER-TCAM error detections and correction method, okay. So now we can verify the Verilog HDL coding, okay. So here this is a test bench of this code, okay. So here we are given a input is search address and will be get the output is match address and match data. Here the search address will be incremented on here using data rich registers, okay. So this is a top model, okay. So this is a code for 64x40, okay. So here initially we are given clock, reset, and input is search key and output is match address, match data, okay. So in this case the two models will be handled on here. One is for ER-TCAM error detections, another one is for ER-TCAM error correction, okay. So in this ER-TCAM error detection we are having write enable 0 and write enable 1 2 3 4, okay, and write address 0 1 2 3 4, okay, and write data 0 1 2 3 4. So depends upon the n size operation will be choose a SRAM here, okay. So it will be vary the 64x40 and 512x40, 1024x40. So it will be very different sizes, okay. So here we are choose the 5 write enable, 5 write address and 5 write data, okay. So here the SRAM memories will be called out here, okay. So SRAM memory is 64x8, okay. So here the write enable, write address, write data and search key, read data, everything will be given on here, okay. And this is a code for error correction method, okay. So here the AGU control unit will be given on here, okay. So it will generate the address, okay, and with support of mod D counter, okay. So here the code will be given, okay, mod D counter, okay. With support of this mod D counter it will generate the addresses, okay. So write addresses and write address BET means binary encode table, okay. So this table memory will be given on here, okay. Finally this is a ECV computation unit, okay. This architecture, okay. Now we can verify the simulation part, okay. So here this is the simulations we are done with the modelism software. So initially the search key will be given on 0, okay, and the match address and match data will come out on 0 versus X, okay, don't care operation, okay. So once the write address and write enable and write data process will be finished in the TCAM memory, okay, in the TCAM memory, then we will be start the search key address, okay. So once the write operation will be finished, okay, so in the all the memory, okay, here AGU, right, AGU address generation control unit, okay. So it will generate the write address, write data and everything, okay. It will return into the memory of error detection, okay. So once it will be finished, okay, we will be given a done flag, okay. So after that the search key will be given on here, okay. So once the search key will be started, okay, so once the search key will be started on here, okay, so it will be come on SRAM error TCAM 64x40, okay, and it will be given to error detection, okay. So this simulation code, okay. So once the search key will be came, it will generate the data, read data 0, read data 1, read data 2 3 4, okay. So this read data will be matched on error encoder, okay. So here it will be matched out, okay, and it will be generate a match information key, okay, and base address registers and bit pattern registers, okay. So these three things will be given to error correction, okay, match address information, base address, bit pattern, okay. So error corrections code, this error corrections code will given this data to mod D counter, binary encode table and ECV computation. So this ECV computations will be match the parity checking values. Okay, P register is the parity checking. Okay, and once it will be match, okay, so the data match will be came. Okay, this data match will be given to match data, okay, and match address. Okay, so once it will be match means the data will be came on here. Okay, so here the match address is 22 and match data is 169.76. actually the data will be sampled on one clock cycle. For 22 the data will be 176. okay, so now we can verify the same 22 on writing part. Okay, so here you can verify the same 22. The output is 169, 176. 176 will be written on 22. Okay, so it will be searched on correctly. Okay, so now we can verify the Xilinx synthesis report. Okay, so here you can verify this is a synthesis report of number of slice registers, number of LUTs, number of occupied slices, and the number of IO bits, and how much memories we are used, number of 18K block RAM used 6. okay, and average fan out effect. Okay, and the synthesis report given on here for delay analysis. Here delay will be taken 1.744 nanosecond, and you can verify the RTL schematic of 64x40. okay, this is a RTL schematic. Okay, so the search key will be given on error detection code. Okay, so here, okay, so once it will be came the search key, every search key will be given to all the memories. Okay, SRAM 0, 1, 2, 3, 4, 5. okay, so all the memories will be given. Okay, so the output of the memory will be given to error encoder. Okay, so this error encoder will detect the operation of error detection. Okay, and it will be generated base address registers, bit pattern registers, and match information register. Okay, so and it will be given to error correction code. So this error corrections code will receive these 3 bits. Okay, and it will be given to error computation unit. Okay, so this error computation unit, okay, will verify this data. Okay, with support of binary encoded TCAM table and AGU control unit. Okay, and it will given a match address and match data to the final output. Okay, so this is a RTL schematic explanations. Okay, once it will be finished you can verify the power report. Okay, so here this is a power report of 64x40. okay, the same thing will be repeated on code 2048. okay, cross 40. okay, so this architectures comparisons will be given on the comparison document. Okay, this is a comparison document. Here we are design 64x40, 512x28, and 512x40, 1024x40, 2048x40. so here the block RAM of 18 KB will be given on here. Okay, and slice registers, LUTs, occupied slices, number of IO bits, delay, and power. Okay, so this is a comparison chart, and all the screenshots will be given on here. Okay, so based upon that we are 64x40 coding and simulations will be given on this video, and 2048x40 the synthesis report will be shown on here. Okay, we are having all the codes here. You can verify the RTL schematic of 2048x40. okay, so here the SRAM size will be different. Okay, 2048x40, and the address size, okay, will be different. Okay, but the architecture of the method will be same. Okay, and we are written an abstract document for this project. This is a base paper abstract, enhancement of this project, proposed title, proposed abstract, existing system, disadvantages, proposed system, advantages, literature survey, finally references. Okay, thank you.